Welcome back to our channel, where we explore fascinating topics and uncover their practical applications. Today, we're diving into the captivating world of graph theory and discovering how it helps us solve complex problems with elegance. So, grab your thinking caps, because things are about to get interesting. Graph theory, in its simplest form, is the study of graphs. Now, I'm not talking about those bar graphs and pie charts we often encounter in data analysis. In mathematics and computer science, a graph is a collection of nodes or vertices, connected by edges or arcs. These connections hold a wealth of information and can be used to model various real-world scenarios. Graphs are incredibly versatile, and they can be used to represent a wide range of systems. Whether it's social networks, transportation networks, computer networks, or even molecular structures, graph theory provides us with a powerful toolset for analyzing and solving problems. One of the most remarkable aspects of graph theory is its ability to capture relationships between objects. Let's say we have a social network, where each person represents a node, and the connections between them represent friendships. By studying this graph, we can analyze how information spreads, identify key influencers, or even predict the likelihood of new connections forming. Now, let's employ the principles of graph theory to unravel this captivating puzzle. Imagine a musical concert featuring 6 incredibly talented pop music artists. Each of these artists possesses unique qualities that set them apart. But here's where it gets interesting. Within this group, every pair of artists either shares a mutual affection or harbors mutual hatred towards each other. In this tightly knit circle of artists, there is a curious rule. It is impossible for any trio of artists to share mutual affection. So, here's the big challenge. Can you prove, beyond a shadow of a doubt, that there must exist at least one trio of artists who mutually hate each other? This puzzle might seem tricky at first, but fear not. We'll break it down step by step, analyzing the relationships and applying the principles of graph theory to unravel the solution. So, get ready to exercise your brain cells and join us on this captivating journey. To help you solve this puzzle, I have provided the following hints. 1. Attempt to transform this puzzle into a problem in graph theory by creating a visual representation of the relationships among the 6 artists and converting them into a planar graph. 2. Apply the pigeonhole principle, which states that, if there are n pigeon-sized holes available in a container, it is impossible to accommodate more than n pigeons in that container without having at least one hole containing more than one pigeon. Please take a moment to engage in solving the puzzle. Feel free to pause the video if necessary. By considering the 6 artists as points on the graph and representing the mutual love/hate relationship between any 2 artists as edges connecting these points, we obtain a graph that exhibits the following structure. Please note that for illustrative purposes, the edges are depicted as gray, but according to the puzzle specifications, each edge can only be of 2 possible colors. Let's assign the color blue to represent mutual love and the color red to indicate mutual hatred between the artists. Consequently, we observe that every edge in this graph is exclusively either blue or red in color. Hence, the problem now transforms into demonstrating that if there is no instance of a blue triangle within this complete graph, then there must exist at least one red triangle. Consider selecting an arbitrary point, denoted as A, from the graph. According to the pigeonhole principle, out of the 5 edges connected to point A, a minimum of 3 edges must share the same color. I encourage you to visualize and verify this assertion. Let's examine 2 cases. Case 1, suppose the 3 edges originating from point A are all colored red, as demonstrated here. In this scenario, if we consider the triangle formed by the endpoints of these 3 red edges, denoted as CDE, we can confidently assert that not all 3 sides of this triangle are blue. This conclusion follows from the absence of blue triangles in the graph. Thus, at least one side of the triangle, such as side CD, must be colored red. Consequently, we observe that the triangle ACD comprises exclusively red sides, confirming the existence of at least one red triangle within this graph. Case 2, suppose the 3 edges originating from point A are all colored blue, as illustrated here. In this situation, if we consider the triangle formed by the endpoints of these 3 blue edges, denoted as CDE, we can definitively state that all three sides of this triangle are red. This certainty arises from the fact that if any one of these three sides were to be blue, let's say side DE, we would encounter a contradiction where the points ADE form a blue triangle, which contradicts the puzzle's conditions. Thus, we have once again established the presence of at least one red triangle, namely CDE, in this graph. In conclusion, we have successfully solved the puzzle by leveraging graph theory and applying the pigeonhole principle. By visualizing the relationships between the 6 artists as a graph, we demonstrated that if there are no blue triangles present, there must exist at least one red triangle. Through careful analysis of 2 cases, we confirmed the existence of a red triangle in both scenarios, thereby proving the puzzle statement. This approach showcases the power of mathematical principles in solving complex problems and highlights the fascinating interplay between graph theory and logical reasoning. Thank you for watching. If you enjoyed this video, kindly show your support by clicking the like button and subscribing to this channel for additional related content.